Okay, I'm going to try to keep this a lot shorter than my last video, and we're just going to pick up where we left off. So this was the last slide we did on Friday. Let's recap. We talked about digraphs, and we talked about how they represent scheduling, and we ended with something called project digraphs. Okay, project digraphs are what we're going to be used for our scheduling type problems. And we're going to talk about the basics of scheduling today and what it means. Remember that we always have a start point, we always have an end point, okay, and you're going to have your task list with some type of letter or something like that, and you're going to have the processing time give in parentheses, okay. Remember that the start and end are imaginary tasks that just help you see the path through the task, okay. Um, Remember that precedence relationships talk about things that have to be done before you move on to something else, like showering to then dressing. Okay, so just keep all that in mind. We're going to use that kind of stuff today, talk about the basics of scheduling. Okay. Okay, here's an example of a scheduling type problem. All right, so you wreck your car. There are 4 pairs that need to be done, and there are 2 mechanics. Remember yesterday we talked about how the people that are doing the task are called your processors. And I don't know if I spelled that right, but processors. That means the people that are doing the task. So we got 2 people working. They're going to be working on 4 things. And it says that the exterior body work must be completed before painting and exterior work can begin. All right, that's task A and task C. So that's your only precedence. A, which is the exterior body work, which takes 4 hours, has to be done before C, the painting and the exterior work, can begin, which makes sense. You don't want to do exterior work until you actually fix the body. Okay? You also have to do engine repair, which takes 5 hours, and transmission repair, which takes 3 hours. And you got 2 people working on it. All right, below these 4 charts here show the different types of schedules we can have in this example. Okay, the numbers up here, 0, 1, 2, 3, those represent your time, your hours. Here's your processor 1 and the tasks that he does, and your processor 2 and the tasks that he does. Okay, this is just a way that we're going to represent the task being completed before we turn it to a digraph. Okay, so in this first example here, right here, it seems like we could do much better than this. Look what's going on. Task 1, A, is being completed by processor 1. It's taken him 4 hours. Now remember our tasks, remember from yesterday, our tasks are not going to be divisible among 2 people. So only processor 1 can be working on task A, and then only processor 2 can be working on task B. All right, they can't help each other out. So P1 is working on A while P2 is working on B. Whenever P1 finishes after 4 hours of working, he moves on to task D for 3 hours. Whenever P2 finishes task B at 5 hours, he moves on to task C with 7 hours. So look at this. There's nothing left for P1 to be doing while P2 is working on task C. So he just sits there idle. Okay, so it works good that they're able to overlap that way, but notice the issue here, he's waiting while he's working on P2 is working on C. Alright, so we're trying to reduce the amount of idle time as possible, and P1 cannot help P2. Let's look at the next example. This is an example of an illegal schedule. Alright, because look at what's going on. P1's working on task A, which is great. P2 is working on task D, which is great, but when he's done with task D, he moves on to C. Do we see the issue here? A and C cannot be worked together and overlap. Between 3 and 4 hours, they're working on at the same time. That's impossible because remember of the preference schedule A to C. A has to be completely done before you can move on to C, so that's an example of an illegal schedule. Here's something that's a little bit better. P1's working on A, P2's working on D. He's idle for a little bit. All right, then at hour 4, they're both working on B and C. Okay, the reason he went idle is because he had to wait to work on C before A can begin. All right, and there's 11 hours is the finishing time here, whereas before the finishing time was 12, so it's a little bit better. This is another example where it gives you the same finishing time of 11. Okay, it divided up the task this way, but it's still the same finishing time. Okay, so due to the precedence relation that A has to be done before C, we cannot do any better than the finish time of 11 hours, because 4 hours for A plus 7 hours for C is going to equal a total of 11 hours. There's no way to finish before that because of the precedence. This means 11 is what's called a critical time. Critical time for this project. Every project is going to have an absolute minimum time, which is what critical time means. Critical time is the absolute minimum time. In this example, I just give you a situation where you have a task list, all right, given in these charts right here. It might be kind of ugly to see on your paper if I didn't copy well, but I'm giving you the tasks with the abbreviation and the amount of time it takes to do those tasks, plus the precedence relationships. Okay, so I'll let you read through this problem yourself. It's about building a dream home on Mars. It's talking about all the different tasks you need in order to do that. Then this information is transferred to a diagraph. Okay, so this diagraph is from this chart. All right, if we make a project diagraph, it is much easier to see which tasks are ready from the start and which tasks will have to wait to start. Which task could be started right away? Well, remember, it's the ones that don't have any preference, all right, or any precedence. All right, it's the ones that don't have any precedence in it. It's the ones that start at the very beginning. It's the ones that our start is pointing to. Those are the ones you can complete without any precedence tasks. So what's that? AP, AF, AW, and AD. So I'm just giving an example of a project diagram and being able to recognize tasks that can be started right away. We did an example on Friday with the calculus classes and the math classes and creating a diagram. Let's do an example of creating a project diagram from a chart. Okay, a project diagram. So draw a project diagram for a project consisting of 6 tasks, A through F, that's described by the following table. All right, I'll let you kind of pause this as you go along, but I'm going to go through this example and just explain how I start these off and what I do as I go through them, okay? I always do a project diagram left to right, okay? Everything's always going to be pointing that way. That's kind of how I like to do it. You always start it out with a start, okay, that has a processing time of 0. Whenever you're doing this project diagram, you got to have the letters and the processing time in parentheses. So then the start is always going to point to the tasks that are ready to go. In this case, the ones that have no precedence that are ready to be started are A and B. Okay. Now, from each letter, we're going to go based off of that. If I look at A, okay, A is going to be pointing towards C because A is a prereq for C. C with a processing time of 5. Another prereq for C is B. B has to point towards C. Okay, so we're going based off of that precedence chart. Okay, we're done with A, B, and C. If we go to D, D's only prerequisite is C with a processing time of 1. All right, so those numbers represents how long it takes for those tasks to be completed. Okay, so we're done with D. If we move on to E, E's only prerequisite is D with a processing time of 4. Okay. Now moving on to F. F's only prerequisite is B, so B is pointing towards F with a processing time of 8. So, and then that's it. All right, whenever you get down to it and you get down to your last vertices that aren't pointing to anything, that means those two have to be completed before you end. Okay, so there's an example of doing a project diagram from a table. Okay. All right, so once we have a project diagram, we've got to be able to assign tasks to these processors to complete. Okay, so we're going to be able to schedule with what's called priority lists. Okay, what tasks are priority over others? So nothing in the project diagram actually tells us how to schedule. We could randomly approach the schedule just following the precedence relations, but it would be better to have some type of plan. Okay, so we want to be able to know what task should go first, and we should know who should do what task, and so forth. All right, that's where we get what's called a priority list. A priority list is a list of all the tasks prioritized in the order we prefer. Okay, the order we prefer to execute them. For example, a priority list could be W, X, Y, Z. If we had to make a choice between W and X, we would choose W, okay, because W has a better priority. We can only do W, though, if it's ready to be done, okay? If W is not ready, we would skip over it and move to the next ready task in the priority list. If there are no ready tasks, the processors would sit idle, we saw that before, until something changes. And you can ignore this notation. I do not do this notation with it, and it's not necessary to teach. These are the last type of examples we're going to use today or learn today before we pick right back up with this tomorrow. Okay, so follow along. I'm going to give you a project diagram, and we are going to be scheduling this project to our 2 processors here below with the project diagram shown to the right. Okay, we have 2 processors, P1 and P2, and we are given a priority list. So this means that I want A to be done before B, before C, before D, and before E. That's the order I would like to go in. Okay? So, let's go through this example. Alright. A is the first thing I want to do. So I'm going to look at my project diagram. Here's A. We got to ask ourselves, is that ready to be done? The answer is yes, it is ready. We're coming straight from the start. There's no precedence. So I'm going to give task A to processor 1. All right. Each of these boxes here are going to represent hours. Okay. So processor 1 does A all the way for 6 hours. Okay. After the 6-hour mark, he's done working on A because that's A's processing time. Okay. The goal here is to try to keep it as far left on this chart as we can because we're trying to decrease the amount of time worked on this project. We want to have a small finishing time. Okay, but we got to follow the priority list. All right, so then we've done A. If we look at B, B is also ready, okay, because it's right there at the start. So the farthest left we can go is all the way over here at P2. It's okay for A and B to overlap because one's not precedence of the other. So P2 is going to work on B for 5 hours. And after 5 hours, he's done. All right, so we've done B. If we look at C, C is also ready because there's no preference. We want to give it to the dude that's farthest left, all right, that's able to work on it, which in this case is P2. Okay, because we can start at this line instead of up here. Okay, so P2 works on that task C for 7 hours. 1, 2, 3, 4, 5, 6, 7. And we're done with C. And like I said, it's okay that A and C are overlapping because there's no precedence there. Moving on to task D, we're going to look at D. All right, D is right here. So as long as A and B are both completed and both to the left of D on this chart, then it's okay to put D down there. D cannot overlap with A or B before them. So if we notice A and B both in right before hour 6, so it's okay to go ahead and give task D to processor 1 because it's not overlapping A or B, it's after both those tasks. So I'm going to give it to P1, 2-hour processing time, and we're good. Finally, the last task is E. Okay, E has a precedence of C, which means we cannot do anything to the left of C. Okay, we can't do anything to the left of C on this chart because C hasn't been completed yet. So, how that's going to work is it can't go right here. So this entire time right here, we say that this dude is idle. Okay, and then once we reach this point, either P1 or P2 can work on task E because it's both after C. We'll just give it to P1 since he's been idle for so long. Why not? It doesn't matter. We get the same answer. And that's a processing time of 5. 1, 2, 3, 4, 5. And we'll just say this dude was idle until the end. Okay, because they can't work together on the task. So that's where it ends. We've done our task. That's the last hour we have. It took 17 hours to finish. Yay! All right, I've reached 17 minutes. Okay, I got 3 more examples on this paper I was wanting to do with you. I promised you I wouldn't go past 17 minutes or 15 minutes. I'm at 17. So you can stop the video now and start working on your worksheet if you want. But I'm going to go through the next couple examples for those that still need it. All right. The next few are the same exact type of problems, but with different priority lists. So like I said, I'm doing these examples. If you feel comfortable with these, go ahead and get the worksheet and begin on it. If not, here's some more examples, okay? I'll go through these kind of quick, and I'll continue to go over more of these tomorrow. So if you feel 100% lost, it's okay. We can do more tomorrow. Okay, next example. This is with the same type of project diagram, but with a different priority list. So see what happens here. Okay, so we start with E. Let's find E on here. Okay, well, E needs to have C completed for it. So we're just going to skip E because E can't be done yet. All right, so moving on to D. All right, if we look at D on our graph here, it looks like that A and B both need to be completed before we do D. So we're going to have to skip that as well. E and D are both not ready. So if I go to C and look at C on our graph, well, C is ready. It's coming straight off the start. It has no precedence. So we're going to give P1 C. 1, 2, 3, 4, 5, 6, 7. And a processing time of 7. So we're good with C. Once you finish with a task on your priority list, go back to the beginning. See if that makes it so you can do one that you previously skipped. So if I look at E, E has a precedence of C, so that means I can do E now. Okay, that's good. But I can't put E right here with P2. I can't have it overlap with C. It has to be completed after C. So why not just, I can put it either here or here. I suggest keeping it with P1 because we don't know how much space we need to leave for P2. So I'm going to give P1 those 5. Okay, so that's good. All right, moving on to D. Well, D still requires that we need A and B, so we're going to skip it and go to B. B is ready. That's good. So B has no precedence, which means I can give that to P2. 1, 2, 3, 4, 5. All right, going back to D, I still need A to be completed, so I'm going to skip to A. A is ready, and I'm going to give that to P2 as well, because there's no need for overlap there. You can overlap with anything. And that's the farthest left that goes with P2. 1, 2, 3, 4, 5, 6. Yay. So now D is able to be completed. D has to be past B and A. All right, so the point that you can do that closest on this chart is right here. Okay, so I'm going to give this D and D. And this is where we finish. This is the point when all the tasks are completed. Right here, this dude was idle. Okay, so in this case, it took 13 hours. In the previous example, with the same exact, that was the bell. I hope everybody's sitting down. Stay quiet. Oh, shut up, Chris. Okay, sorry. Okay. So this was the same exact project diagram, but with a different priority list. It gave us a finishing time of 4 hours less than what we had. So it all depends on the priority list that you have. Okay? The difference in this example is like, let's see what happens if you have 3 processors, 3 workers, and the same priority list, the same project diagram. So this is the same exact one as trial 2, but with 3 processors. That's the only thing that's changed. So let's go through it. All right, looking at E. Can I do E? No. So I'm going to skip to D. Can I do D? No, because I need A and B. So I'm going to skip to C. Can I do C? Yes, I can do C. So I'm going to give that to P1. 1, 2, 3, 4, 5, 6, and 7. All right, so we're good there. C's out. Going back to E. Can I do E? Yes, because C has been completed. So I'm going to do the same as I did before. I'm going to go ahead and give that to P1 because it can't go over to P2 or P3 underneath C because it can't overlap with C. So I'm going to give him 5 E's. All right, cool. E's out. Moving on to D. Can't do D, so I'm going to skip to B, which is ready to go. And since it can overlap with anything, I'm going to put it to P2. Why not? 1, 2, 3, 4, 5. All right, can I do D? No, so I'm going to skip to A. A has no preferences as well, so I'm going to go ahead and give it to processor 3 because he's the farthest left I can go. 1, 2, 3, 4, 5, and 6. So A's done. Now I'm going to go back to D. D can be completed once A and B are over, and they are. As long as D is to the right of A and B, I'm good. At this point is when we are to surpass A and B. It can't be anything before that. So this dude's going to be idle right here. So it doesn't matter who you give it to at this point. Just for the heck of it, I'm going to give it to P2. D, D. And that's it. Okay? He's idle the rest of the way. And he's idle the rest of the way. And they all finish at 12 hours. Okay? So as you see, we went through those 3 examples with the same project diagram. We changed the priority list. We changed the amount of processors. So the question is, how do we decide what priority list is best to use in order to give us the smallest finishing time? In a project diagram with n tasks, there are n minus 1 factorial possible priority lists. Okay? So there's, with 5 tasks, we would have to check, using this formula right here, 120 lists to find an optimal answer. Okay, we're going to have to find some efficient algorithm to give us the best priority list possible. Okay? And we're going to go through that tomorrow. I mean, I'm done with the lesson, but here's the last example. I'll probably go over this one tomorrow just for warm-up, or maybe another one like this, but if you want to listen to me doing it, you can. Schedule the following on 2 processors using a given priority list. Okay, so starting with C. Can't do it, all right? Too many precedents, so I'm going to skip to B. All right, B, let's see, can I do it? Man, I can't read that. No, I can't do B. It's right here. So I'm going to skip to E. Can I do E? No. Can I do D? Yes, I can do D because that's the first one that's ready to go. That's with a processing time of 3. So I'm going to give P1 3 Ds. Okay, E's out. Starting back at C, still can't do it. Still can't do B. I can do E now because I've already completed its precedence. So I'm going to do E. It has to be after D. So I'm going to go 1, 2, 3, 4, 5. Okay, so E's out. Can I do C? No. Can I do B? No. I can do A though because that one's ready to go right here. So A has no precedence, so I'm going to give it to P2. And now A's out. Can I do C? No. Can I do B? Yes, because its precedence has been done. It has to be after A. So I'm going to give 3 B's after A. And now he's out. Can I do C? Yes, I can do C. He's got to be after after A and B. So it really doesn't matter where he goes. Okay, I'm going to give him to P1. 3 C's. And lastly, I'm left with F with a processing time of 4, and it's ready to go. Doesn't matter where it's go, so I'm going to put it as far left as possible right here. We have a finishing time of 12 hours. All right, now I'm officially done. You guys are awesome. I love you all. Okay, bye. Oh, and if you have any questions on this, trust me, we'll go over a lot of it tomorrow. I just want us to have a good basis for where we start tomorrow. Okay, bye.